This is the 37th lecture of the course MTH 204A for section B. Recall that we were discussing the basic properties of characters of representations. So let me call for you that for any finite group G and a finite dimensional complex vector space V, if rho is a representation of G on V, then the character of rho is defined like this, that is the trace, I mean at any point G, chi rho, G is the trace of the operator rho G. Then we have seen that this group algebra of this group algebra CG is as a vector space, this is isomorphic to Cn, hence we can by considering the natural inner product structure on Cn, by considering a very natural inner product and bringing it to here, and then by an appropriate scaling by scaling it appropriately, we obtain CG an inner product space like this, okay. And with so this is, as I have already said, that this is nothing but the pullback of the usual inner product of Cn scaled appropriately. And with respect to that inner product, earlier what we have proved that the irreducible characters of G, they form an orthonormal system or orthonormal set, orthonormal subset of CG. Since CG is after all a vector space of dimension n, and in any product space the any orthonormal set has to be linearly independent as well, in particular any orthogonal set. So from this it easily follows that, so this set, so that is if corresponding to each up to isomorphism corresponding to each isomorphism class of representations, if we consider its character. So recall that when two isomorphism, when two representations are isomorphic, then their characters are going to be same. So like for corresponding to each isomorphism class of representations, if we consider its character, then the set of all such characters, that set has to be finite, because since that subset will be an orthonormal subset of CG, hence it has to be finite. So from here it follows that, so given finite G and all this, they up to isomorphism, there is finitely many different representations, different irreducible representations, okay, because they are because corresponding to each such representation, if we take its character, then the set of such characters will form an orthonormal system. So this is what we obtain. So for the rest from now on, or for in what follows, let's assume that, so we have only finitely many isomorphism classes, right? So we pick one from each class. So assume let wi rho I are finite dimensional, are, so let me put it here, I from 1 up to k, are all distinct means, okay, I should rather put mutually non-isomorphic finite dimensional complex representation of the finite group G, okay. So what we have done is, corresponding to each isomorphism class, we have taken one representative, namely a representation, and also let chi I denote the character of rho I for every I. Okay. So, now let's consider an arbitrary complex finite dimensional representation. So, let V be a finite dimensional complex representation over C. By Marshki's theorem we can, so in view of Marshki's theorem, V will be some UL. So, each UI is a G invariant subspace. Okay. G invariant subspace, and we have already seen that another way of putting this is the following, that so let since this is 0, so let okay, so let me call it psi, and let psi I be the sub representation of psi on UI for each I. So, what we are doing is, how is that defined? Psi of I of G is defined as psi G. We defined it on UI for every I and G. So, this is just the restriction operators. So, okay, psi A is there, and let us also denote the characters of this character of psi I. Well, let us denote this by, for that I mean something like let us say some let us denote the character by phi I. Okay, I hope I have not used this notation here. So, phi I is the character of psi A. So, yeah, fine. This is the character of psi I. So, we have already seen that V is the direct sum of these G invariant subspaces. Another way of putting this is basically saying that the representation rho is isomorphic to the direct sum of these representations. Okay. So, this is also what we have seen. So, hence this what we obtain from here is character of psi is nothing but, so I should have said psi 1 up to psi L. So, character of psi will be psi L, and remember that is the so all these are G invariant irreducible subspace. So, therefore, what it means is this each psi I is irreducible, hence their characters are irreducible characters. Okay. So, now what follows immediately is this, that for each j from 1 up to k, it follows that for each j from 1 up to k, so chi psi and chi j is basically these products, because of the inner product. So, this is I from 1 up to L phi I chi j. So, what about each of these terms? By our assumption, all these chi i's are irreducible characters, and here phi i's are also irreducible characters. So, therefore, if you look at any typical summand, it will be either 0 or 1. So, therefore, I mean the terms which are 0, they are anyway going away. So, therefore, the right hand side is precisely, so the right hand side precisely denotes the number of I such that psi I is isomorphic to rho j. Okay. So this is for any j. So what we do, again let me repeat what I am doing, corresponding to every j. So we have already fixed representatives from each of all the equivalent isomorphic class of finite dimensional complex representations. So these are denoted by W rho i's, and let's take the underlying space on which the representation is taking place is Wi. So therefore, once we do this character considerations, then in this in these decompositions, the number of subrepresentations. So in this decomposition, the number of subrepresentations which are isomorphic to the given rho j, that number is there on the right hand side, right? Now look at the left hand side. Left hand side is just the character of this representation and rho I. So surprisingly, the left hand side is independent of the decomposition. Okay, I think I should explain more. So given a representation, finite dimensional complex representation, Marshki's theorem says that we do have such a decomposition. But as I have already said, if you remember, this decomposition need not be unique. Let me give you a very, very quick example. So suppose your representation, let's say your vector space is C2 and the representation is trivial representation. Then if you take any two lines passing through so if you take any line passing through origin, that subspace in the representation is trivial, it is going to be certainly, you see, it's going to be certainly G invariant, and therefore this representation, so therefore this is a decomposition of the representation into the sub-representations on L1 and L2. You see, whichever L1 and L2 you choose, any two distinct lines passing through origin, that will work. So it shows that it's just a, of course there are other much more I would say, like this is a very trivial example, there are other quite non-trivial and significant examples, but just for now let's make ourselves happy with this only, because the main point is that Marshki's theorem only allows that there will be a decomposition, but that decomposition need not be unique. Okay, so one might be having another entirely different set of irreducible G invariant subspaces whose direct sum will be such that V can be written as a direct sum of those subspaces, or in other words, one might have a different set of irreducible sub-representations such that the given representation becomes same as the direct sum of those sub-representations. Okay. So the main point is that we cannot expect, we should not even the uniqueness in the decomposition. But however, this consideration shows that like there is some sense of uniqueness there as well. So let me explain more. So if you take any decomposition into irreducible subspaces, in that decomposition corresponding to each rho j, the number of subspaces in that decomposition, the number of summands which are isomorphic to this rho j, that number is, we see thus from the orthogonality relations of characters that number does not depend upon the decomposition we have considered. So in other words, suppose two people are given these tasks of decomposing a given representations into irreducible sub-representations. Now and they assume that there is no communication happening between them. So therefore possibly they will end up with two very, very different decompositions. However, what we can see that for each rho j, so the number of sub-representations which are isomorphic to the first to the decomposition of the first person has to be same as that of the second person. Okay. So thus, as you see that like though these subspaces are not unique, though the sub-representations are not unique, but however, whatever decomposition you choose up to isomorphism, there is a uniqueness in the sense that, so if these if these are my all irreducible irreducible representations of G, then each irreducible representation, I mean number of times that occurs in a given decomposition is actually independent of the decomposition, right? That is what, I mean that is exactly what we have seen. So therefore we put it in this way. So like as I said, number of psi i's that are isomorphic to any given rho j is independent of the decomposition. Okay, this is what we have observed. Therefore, as I said, if two persons are doing the task of decomposing a given representations in independent manner, however, what will always be there is up to isomorphism, like they will have the same summands, and not only that, the number of occurrences corresponding to each summand, of course up to isomorphism, will be the same. Okay. So in much more formalized language, as I said, that if we want to see that how many sub-representations are in the decomposition of the first person isomorphic to a given irreducible representation, so that will be exactly same as that of the second person. So in this manner, so I mean if we want to be little bit sloppy, so the number of times this rho I that occurs in the decomposition, that is unique. In fact, for our convenience, let us define like this. So we define this terminology. So given an irreducible representation, lambda of G, finite dimensional representation, of course, finite dimensional over C representation, number of times lambda occurs. So this is what we define as in a decomposition, the number of sub-representations which are isomorphic to lambda. Okay. So we take a sub-representation and then we see the number of summands, we take a decomposition and we see the number of sub-representations which are isomorphic to lambda. That number, we call it as the number of times lambda occurs in rho, sorry, what's the psi? Lambda occurs in psi. Okay. And we are already convinced that this, in order to find this number, whichever decomposition you choose, that the number actually does not depend upon that choice. Okay. So as I said, for simplicity, from now on we will keep using this term. So like whenever we are considering a decomposition of a representation of G, we will safely look at the number of times each rho I is occurring in that representation. Okay. I hope I have made my points clear. So as I said, though there is no uniqueness, there may not be any uniqueness of the subspaces, however, up to representations, up to isomorphisms, the summands, the sub-representations, those summands are equal, and in fact they occur same number of times throughout, same number of times independent of whichever representation you choose. Anyway, so this of course as I said, that establishes the uniqueness of decomposition. Therefore, what we observe is, given any representation psi, so psi has to be isomorphic to. So first what we do is, like we will recall that we have already chosen these are our all distinct non-isomorphic irreducible representations. So therefore, some of these sub-representations will be isomorphic to some of these sub-representations. So the point that I want to make is, if we look here, so in this direct summand, in this direct sum, some phi i's will be isomorphic to, let us say, rho 1, and that number will be exactly the inner product. So and so on. So therefore, what we have seen is, so any representation psi is actually isomorphic to the following: m1 chi 1, m2 chi 2, m1, I should not say m1 rho 1 direct sum, m2 rho 2, mk rho k, where each mi is nothing but the character nothing but the right. Okay. So whatever representation we choose, so that is up to isomorphism. It must be this, where each mi's are determined solely by in terms of the character of the given representation, and the irreducible, and this, I mean, already chosen irreducible representations. Okay. So as a corollary to this, it follows that if two representations, so here all the representations unless otherwise stated, they are of finite dimension and over C. If two representations have they have the same character, then they are isomorphic. Okay. So that is actually very immediate here. Why? Because like given any representation psi, its character is thus nothing but, so this as I have already observed, this is nothing but okay. This is what we have. So now okay. So therefore, if two representations, let us say psi and psi prime, have the same character, so then it is easy to see that from this it immediately follows that the because they are characters, and this chi i's, they already form an orthonormal set there. So therefore, these scalars have to be unique. So that so this for all I, okay. And what is this? This is exactly the number of times rho I occurs in psi, and this is same as the number of times rho I occurs in psi prime. So therefore, this forces psi is isomorphic to, of course, these numbers, these numbers. Okay, and the same for, because these are the same, because these numbers are same, and that is exactly we have seen, and that is exactly we have seen the psi prime. Okay. All right. So because the main point is that given any representation, finite dimension complex, these MIs are uniquely MIs are uniquely determined. Okay. So these MIs are uniquely given any psi, these MIs are uniquely determined. So therefore it is quite clear from us that psi is exact isomorphic to this, and that it has to be isomorphic, and it has to be same as this, because this I mean this coefficients are the same, and that's exactly the isomorphism type of psi prime. So thus we have seen that two representations, they are having the same characters if and only if they are isomorphic. Earlier we just obtained one direction. Okay. Now I will just deduce one further corollary, and afterwards I will move ahead. So as I said, take psi is if psi is any representation, and this is so this is the isomorphism type of psi, then we consider psi inner product of psi with psi. So that's exactly so summation m1. So okay, so psi is, sorry, I have to consider the character of psi. So inner product of so it's what it is going to have be is, so mi is, so okay, so let me put it mi, so this is simply mi square, right, and mi square is nothing but psi chi psi with chi I square. Okay. So like remember that this all mi's are non-negative integers, some of them could be 0, right, or because here you see each term is either 0 or 1. So therefore like this mi is always a non-negative integer, and in fact that is why it is it makes sense to call it the number of times that some irreducible representation occurs in a given representation. So therefore it is a sum of non-negative integers. So I mean sum of the squares of non-negative integers actually, and such a sum is 1. So this sum is 1, this sum is equal to 1 if for some I there exists I such that mi is 1 and mj is 0 for all j not equal to I, right, that is clear. So this sum is 1 if and only if we have this, and what does this mean? Some mi is 1 and all other mj's are 0. That means it will be isomorphic to some rho j directly, okay, because others are 0. So remember, please try to understand that in this decomposition some of these mi's might be 0 depending upon whether it contains any subrepresentation isomorphic to this or not. So this is just like we say that this is isomorphic, we only say that this is isomorphic to this. So note that some of these mi's here can be 0 as well. In fact that depends upon this situation. So now if you see that if one of these mi's is 1 and rest are 0, then that means psi becomes isomorphic to that particular rho I. So that is psi is isomorphic, psi is irreducible. Okay. So what I mean is, if this happens, then that means psi is irreducible. Okay. Conversely, if psi is irreducible and we have assumed that these are up to isomorphism, all irreducible classes, I mean all irreducible representations of G, then psi must be equal to some rho I, and once psi is equal to some rho I, then certainly that mi is going to be 1 because they are going to be the same character, the characters will be same, and certainly all other rho j's, I mean certainly all other mj's will be 0. So what we see is that this condition is also the converse, so this condition is also sufficient. So therefore all total we have obtained that, and a criteria for a criteria for verifying some representation is irreducible in terms of characters. So, what is the criteria? Given a representation psi, we take the inner product of psi with itself. This inner product is 1 if and only if psi is, so psi is irreducible. So, let me simply write that here, and the argument I have already just given. This is 1 if and only if psi is irreducible. Okay, because we have seen that this is 1 if and only if this is 1, in fact if and only if, this is what we have to have, sum of squares is 1, if and only if this, if and only if this, and that is exactly same as equivalent to saying psi is irreducible. Alright, so this is what we see about the decomposition of a representation in view of the orthogonality relations for characters. So, these orthogonality relations are very influential. They provide us with a very useful uniqueness of the decomposition, namely in terms of the occurrence of each irreducible representation. Okay. And as a corollary we obtain that, the two characters, if two representations of same character, then they must be isomorphic, and another one that which is basically a criteria, to solve, necessary and sufficient criterion to see some representation is irreducible. Okay. So, now let us move to something else. So, we now talk about left regular representations. Okay. So, what is left regular representation? Recall, so here as usual our setup would be G is a finite group. Now, the finite dimensional vector space that we are going to choose here is basically this group algebra. Remember, this is a vector space over C as well. Now, recall that G, one can have this action of G on itself by left multiplication. So, recall that whenever G acts on a set X, okay, then that gives us a representation of G on the function space of X. So, here from this action or natural action of G on itself, we obtain a representation of G on the function space of G, which we have already seen, that is nothing but Cg. So, therefore, this action gives rise to this representation, which we call as the left regular representation of. So, is coming from left action, left regular representation of G. So, we sometimes denote this by RG, this representation, and the character of RG is denoted by chi-reg. So, the character of the regular representation. Okay. So, also recall that from the way G acts on this G. So, for each G and X in G, so from the RG of G, this linear operator, when it acts on the vector, so what is the basis of Cg? If you remember that Cg is a finite dimensional vector space. So, a basis of Cg is precisely this collection, okay, basis of Cg So, we have done it more generally in case of any set. So, Rg of this Rg G when it applies to Ex, what we obtain is Egx. Okay, that is what we have already seen. Now, let us come to the computation of this character. So, chi reg of, let us try to calculate chi reg of G for any typical G. So, already we have think this was given as an exercise that for any action of G on X, the permutation representation that we obtain, then corresponding to any linear map, the trace is corresponding to any G. If we look at the linear map corresponding to that G, then the trace of the linear map is number of points fixed by G. This has been done as a general exercise for any action of G on any arbitrary set X. So, and here we have the action left multiplication. So, therefore, chi reg G is basically the number of points. These are fixed once they are getting multiplied by the group element G, and you see that if G is non-identity, that is not letting anything fix. So, therefore, this is what we have the following: if G not equal to identity, and if G is equal to identity, then all the elements of the groups, they are fixed. Okay. So, therefore, we have if G equal to I1 1, and in view of this we see the following, that okay, as I said that throughout I will fix that these are my up to isomorphism all irreducible mutually non-isomorphic all irreducible representations of G, and the character of rho I will be chi I. Okay. So, this is already in our setup. Let us we won't change that. Now, let us try to see the number of times let us see that the number of times each of these sub representations appear in this left regular representation of G. So, this is given by the inner product of the character, right, chi reg, chi I. So, what is this? What is this? So, this is chi reg G, chi I G bar. Okay. Now, as far as this sum is concerned, you see apart from the identity, the term corresponding to G equal to identity, all other terms have to vanish in view of this, right. So, therefore, only thing that survives here is this fellow and chi I of 1 bar, and here this is already we have seen that chi I of 1 is nothing but dimension of Wi. Okay. So, let me also denote by Ni the dimension of Wi. Okay. So, as I said that first we have chosen a set of set of mutually non-isomorphic and exhaustive collections of irreducible representations. So, therefore, here we obtain is the following. So, this is chi reg 1 is order of G. So, this product is just 1. So, simply Ni. Okay. So, what we have seen is each irreducible representation, because these are all after isomorphism, each irreducible representation of G each irreducible representation of G occurs Ni number of times. Ni is the dimension of that representation. So, number of occurrence of each irreducible representation in the left regular representation of G is equal to the dimension of the irreducible representation. Okay. So, rho I will appear in in this RG exactly dimension exactly ni number of times. So therefore, one immediately obtains the following, that chi reg from this chi reg is ni times chi I, okay, chi reg is ni times chi I, okay, and from this we immediately draw two consequences. First one is the famous very well known dimension formula. So if we, so this character is equal to the sum of the, this character is equal to sum of this combination of these characters chi I. Now you evaluate both the sides at the identity. So therefore the first consequence is nk square. So if these are my irreducible representations after isomorphism, then the square of their dimensions must be equal to order of G. That is what we prove, which otherwise would be very difficult to establish. And second thing is like if you evaluate both the sides at some term other than identity, you obtain the following, that 0 equal to ni chi I G I from 1 up to k for any G to identity. Okay. So this is the dimension formula. So this formula is useful in at many places in the following sense, that suppose somehow we are able to construct a collection of mutually non-isomorphic irreducible representations of the given group of a given group G. Now in order to assure those representations that we are somehow able to construct, those irreducible representations are all, that collection is exhaustive, it is necessary and sufficient that the square of their sums will be equal to order of G. So whenever we are somehow obtain such a collection, we then look at this sum of squares. If that is equal to the order of G, then we are completely sure that completely assured that our collection is the collection of all representations. Okay, so now let me get into the discussion of class functions. So earlier we have seen that the set of all this irreducible characters that forms an orthonormal set of CG. So one might ask that whether that serves as a basis or not. Certainly that is not the case. Let me explain to you why that cannot be regarded as a basis of CG. That's very simple actually, because if you see, because like this is what is our collection, right? Orthonormal set chi 1 up to chi k. Now if you remember, each character of a representation has a very special property, that if chi is a character, then Gx G inverse is chi x, okay, for every G and x in G, okay. So therefore if you take any combination of these chi i's, you see those functions they have the very special property that they are going to be constant on each conjugacy class, okay, because this says that on the conjugacy class of x the character chi is constant. So since each chi I is having this property, so does any linear combination of them. So therefore whatever function, I mean, you pick up from their linear span, they have this property that on each conjugacy class they have to be constant, okay. But of course you can I mean, it is evident that there are such functions which need not, there are too many functions which need not be constant on any conjugacy class. So therefore at least this orthonormal set, I mean, we cannot expect that it will be a basis of whole of CG, Okay. But however, this observation that we have just made, that why this cannot be regarded as the, why we cannot even expect that this is going to be an orthonormal basis, that immediately poses a new question, that instead of considering all functions in CG, if we consider exactly those subcollection of functions which are constant on equivalence classes, so then can we expect that that is going to be a orthonormal basis of that subspace, provided we are able to show that subcollection indeed forms a subspace. So that is the very natural question which comes at this time. So we'll see an affirmative answer of this question. So before that, let me define a terminology. So a function from G to C is said to be a class function, is said to be a class function if for every G and X in G, f of Gx G inverse is f of x. So that is, it is constant on every conjugacy class. Okay. So such functions are called class functions, and let us use a very temporary notation. The temporary, the reason for choosing temporary is later on we see that this is actually, I mean the collection, well, so let me first do it. So we denote the set of all all class functions by H. So f is a class function. Okay. So for saying this is temporaries, later on we will see that this H is nothing but the center of the group, this group ring CG, if time permits. But I mean what I just said, that it is going to be the center, that is not so important in what we are going to do. I mean what we aim to do in this course. So therefore, as I said that we will stick to this notation only. I mean if later on time permits, then we will show that is equal to the center of the group ring, just for a completion. So right now, so until that, let us stick to H only. Therefore, yeah, so it is easy to see that this H is a subspace, because the sum of the observation, let me write it, H is a subspace of CG, okay, because the sum of any 10 to class function is going to be a class function, same for scalar multiplication, this is a subspace. And of course, therefore it is also going to be a finite dimensional vector space. So this is, therefore this is a finite, this vector space has to be finite dimensional. We can even exhibit a basis of this subspace. So what we do is, let C1 up to C1 up to, let us say, CR be all the distinct conjugacy classes. So they are distinct conjugacy classes, they are odd mates, so they are going to be disjoint distinct conjugacy classes. Conjugacy classes in G. Also we let that Xi belonging to Ci. So corresponding to each conjugacy class, we define this indicator function, right? So this is the function that takes the value 1 if y is in Ci 0, otherwise, okay. So by its very definition, each of this, so each is in H, right. Furthermore, if furthermore, each f lying in H can be written as follows for each if, so I should say that fx1 c1 fxr okay, because if you take any arbitrary point y, so y must be in one of these ci, so therefore the left hand side it will be fy. So the left hand side fy, since y is one of these, y lies in exactly one of these ci, so fy will be fxi. Now on the right hand side you will see that exactly that term will survive and nothing else, okay, because of the way this is defined. So that shows that every f lies in the span of these functions, this indicator functions of the equivalence of this conjugacy classes, and furthermore it is also easy to see that this set is linearly independent, because the point is that their supports are disjoint. So like if these are my disjoint conjugacy classes, so this is C1, C2, Ci. So since their supports are disjoint, whenever a combination vanishes, then each coefficient has to vanish, okay, because so it's quite easy, right? If alpha I Ci, this sum vanishes, then like if we look at the left hand side immediately, this forget about what is there in the right hand side. In the left hand side, this function, the way it is defined, it takes constantly the value alpha 1 on C1, constantly takes the value alpha 2 on C2, and so on. So therefore if such a function is 0, that means all those alpha i's will be 0, okay. So the linear independence is immediate. So this shows that the indicator functions of the conjugacy classes, that forms a basis of this subspace of class functions in CG, okay. So as I said, not only this is finite dimensional, the dimension is exactly equal to the number of conjugacy classes. Dimension of C is number of conjugacy classes. Okay. All right. Now let's come to the main part. So this is a finite dimensional vector space, and this is an orthonormal subset of H. So we now prove that this is in fact an orthonormal basis of H. So for that proof we have to make certain observations. So I will of course start the preparation for the proof. So if in case I cannot finish this in lecture, of course in the next lecture we will be done with that. But the main observation behind this general observation behind this proof, I would of course discuss today. So what we start with is the following, that as expected, throughout G is assumed to be finite, and these are irreducible representations. So let V be a finite dimensional representation, a representation of G, okay. So these are representations, are complex representations, and F from G to C, and F is in, let F be a class function, okay. So given any representation and a class function, we can let's construct this, the following operator. Rho G, okay. So this is an operator from linear operator from V to V, right. Claim this operator is G invariant. So, try to again understand, given any class function f and any representation v, rho, we can form this operator. So, this is claim is this is G invariant. So, how to prove that? That is quite easy. Let us say rho x inverse rho f rho x, this is exactly what we are supposed to compute, and that is exactly nothing but, so f okay. So, of course, each f is not going to be a problem, f is not going to be a problem here, rho x inverse g x, right, and yeah. So, therefore, try to understand that given, I mean, when x is fixed, then when x is fixed, so then g goes to g inverse x g actually is an automorphism of g. So, therefore, varying g, we basically obtain all the elements of g, perhaps in a different order. So, therefore, we can make this change in the variables, saying that saying this is rho g prime. So, therefore, like g prime we are putting as x inverse g x. So, therefore, g will be x g prime x inverse. So, x g prime x inverse, and as g runs over all elements of g, g prime will run over all elements of this, okay. And now we use that f is a class function, therefore, this quantity must be same as, right. So, thus you see that this is exactly rho f, okay. Therefore, rho f is G invariant, so G invariant linear operator. Now, furthermore, if we now assume rho is irreducible, if rho is irreducible, if rho is irreducible, then by Schur's lemma, this has to be some constant multiple of, so this rho f, which is nothing but has to be some constant multiple of identity, okay. And what is that constant? The constant will be certainly that is obtained by considering the trace. So, we take, so the trace of right hand side will be lambda times dimension v. So, lambda, so this will be 1 by dimension v times the trace of this. So, like if we assume chi is the character of this rho, then here we obtain, I have to just scale it appropriately. F g chi g. So, basically this is order of g divided by dimension of v. So, what is this? This is nothing but inner product of f and chi bar, right. This is what we obtain. So, thus what we have learnt is, if we start with any class function f, then for every irreducible representation, this representation rho f is going to be the constant, rho f is going to be this map, and the constant is precisely this object, okay. So, this is going to be our main observation behind the proof of this. Now, let me start the proof, and The proof is not long. In fact, once we make this observation, things are actually more or less there. So, we have already shown that this system is orthonormal. Okay. Now, we have to show that it is a basis, that is, we have to show that this generates whole H. Okay. So, since we are working in a finite dimensional inner product space, so another way of showing that this spans H is, we will show that anything that lies in the orthogonal complement of this set will be 0. So, that means, in other words, the span, the orthogonal complement of their span is trivial, hence that forces the span is itself whole of H. So, okay, I would say it suffices to show that if F lies in the orthogonal complement of, then F is 0. Okay. So, fine. So, what we do? So, recall that corresponding to this F. So, if we take any I here, then the map, what we have already done. So, this Fg rho I for each, this rho i's. So, rho Ig, rho I is irreducible. So, for each g, this rho Ig, this is going to be a linear operator from Wi to Wi. This is certainly going to be a scalar. So, what is that scalar? Scalar is some g times dimension Vi, sorry, g times dimension Wi times okay, fine. What we will do is a slight, we will just make a very slight change. The reason for making this change you will understand when the proof is over. So, see that if F, I mean let me write it here, if F is in H, then the complex conjugation F bar is also in H. So, recall that how is F bar defined? F bar of G is nothing but defined as the complex conjugation of, okay. So, this H is closed under complex conjugation. So, you rather take this, the advantage will be simply F bar, this will be simply F bar chi bar, this will be okay. Do I need to consider this? So, okay. I think let's see what let me directly write down the quantity. It will be, that will be clear. If suppose if I start with F, so this quantity would be Fg, this would be that quantity, but now actually what we need is according to our assumption, we have here we have F is orthogonal to any of these, so F is orthogonal to any, I mean all of F is orthogonal to all chi i's, okay. So, let me put it bar here. So, we start with F bar instead. So, this quantity is nothing but this whole scalar times okay, dimension. So, this whole some scalar times this So what is there? So this is what we can simply, we can just write as Fg chi bar g, right? This is what we can write easily, that is not an issue. So hence this is nothing but conjugation of, so inner product of this with chi I, okay. So hence this is 0. Okay, I think I should stop here. So the whole, so what we have seen is that if f lies at the, if f lies at the orthogonal complement of this functions, then we would see that these operators will be 0. Okay. So this is what I think that's what we wrote as rho f bar, okay, according to our notation. So what we have thus proved is if f lies in the orthogonal complement of this chi i's, then rho f bar is 0, right. So remember, rho f bar is thus a map from, so I think with that I will just stop. The next lecture I will finish the proof. So I will just made this claim that if f lies in the orthogonal complement of this, then rho f bar, which is by the way we have done, it is a map from Wi to Wi, rho f bar is trivial. Okay. The next step would be, for so here we have this, we have done this. The next step would be that for any representation rho, irrespective of irreducible or not. So here if you see that this, so I should put some I here, and maybe I should put some I here just to distinguish that is coming from I. So for any representation rho, this rho f will be, this is what we are going to show next time. Okay, with that I will just simply this is what we will show. So it just says that for whatever representation you choose, so earlier we have proved this when rows are these rho i's, okay. Now we will show that for whatever representation we choose, this is what is going to happen. The main basis for, I mean the reason for this is that every representation is a direct sum, every representation rho is a direct sum of rho i's. So we will give of course details. So just by using this observation that rho I is the direct sum of rho i's, from that we will show this step, and once this step is over, then we can take rho to be this left regular representation that will finish the proof. Okay. So here I am leaving the proof of this statement somewhere in between. So in the next lecture I will finish the proof and draw and talk about some further, talk about its like some talk about its some further consequences, and then go ahead. Okay, so with that I will finish.